Now, the story of this work is very funny. During the previous cost action, I used the short-term scientific mission to measure some of our superconducting thin films with artificial pinning centers at University of Santiago de Compostela, because our BaFeAsP machine was out of order. So after I did what I wanted to do, I talked with my host, Jesus Mosqueira, and they were investigating some Pnictides. Now, isovalently substituted iron-based superconductor, barium iron 2, arsen 1 minus X, phosphorus X2, is a material that qualifies as an archetypal clean superconductor containing only sparse, strong point-like pins. Now, vortex configurations imaged using, no, this is for, so okay, what is the pointer?
It's on the top.
Oh.
No, there.
Oh, that one, no. Okay. Vortex configuration imaged using bitter decoration method show less density fluctuations than those previously observed in charge-doped barium, iron, cobalt, arsenide 2 single crystals. Pinning force and energy distributions depend on the phosphorus content, X, but they are always much narrower than in barium arsenide iron cobalt single crystal due to the weaker temperature dependence on the superfluid density on approaching TC. The weaker temperature dependence on the superfluid density on approaching TC observed for X033. Hence, this system is the cleanest iron-based single crystals from the point of view of influence of disorder on vortex matters and dynamics. And these are the main things which comes from this work by Demirdis et al., which was published a few years ago. Now, magnetoresistance measurements were performed in a quite range of resistivity. It was used the thermal activity flux flow model, and we got these results here, where we have a flux flow. It had a critical vortex glass and a crossover temperature, and all these things has been published in this paper last year. Resistivity near the vortex glass phase is expected to obey this expression, and it allows the obtaining the dependence of the glass temperature as function of field with this exponent between 2 and 2.5, and our experiments show something an average of 2.3. And my contribution to this work was in terms of vortex melting lines. It is a technique which I developed quite a long time ago for studying some strange thallium and mercury-based superconductors which were made only in high pressure synthesis technique. So the story is that we all know that BM, the vortex melting lines, BM as a function of temperature, of melting temperature as a function of field, separate the vortex glass and vortex liquid phase. Vortex glass, it's a strongly nonlinear dependence of the dissipation on the current, while in the vortex liquid there is an ohmic or linear behavior, so for low current levels there is a dependence of the dissipation on the current. On the other hand, when you do susceptibility measurements with very low AC fields, meaning a very low probing current, to stay at very low current densities, out-of-phase susceptibility is a measure of the total dissipation, which is linear and nonlinear, while the third harmonic is a measure of the nonlinear dissipation only. So if we have out-of-phase susceptibility larger than 0, but the third harmonic component is 0, then we are sure to be in a vortex liquid phase, while when we have an onset of the signal from the third harmonic, we know that we entered in the vortex glass region. So the measurement goes like this. You fix a DC field, and the onset in the temperature dependence of the third harmonic represents actually the melting temperature of the vortex system at that magnetic field. So here are some measurements you see. So the difference between this is that there is a difference in the noise level for the third harmonic as the first signal from out of phase susceptibility. So this is 0.5 Tesla. You see the onset of chi second, and here the onset of the third harmonic, and this happens at all magnetic fields we tried, between 0.5 Tesla up to, I think, 9 Tesla here. So from this we managed to make a quite nice vortex diagram for this single crystal, in which the vortex melting line measured in this way, it's quite close to the theory and the T star where it was observed in the magnetoresistance measurements. After that, I took a couple of single crystals from that batch, and I started to look at a much larger window in the terms of temperature. For that study, I was interested only in the onset of the third harmonic, so we stayed quite close to Tc. So what I observed is, for example, in 1 Tesla, 447 hertz here, almost 10 kilohertz here, so different frequencies. And we have seen some small anomalies in the temperature dependence of out-of-phase susceptibility, so dissipation mechanism, and the in-phase susceptibility. Double peaks in the dissipation signal I have seen in my life. Many of those, it happens if you have a multi-phase sample. It happens if you have a polycrystalline sample and you have the intergrain critical current and an intragrain critical current. So it was not very spectacular. This one was a little bit more intriguing in the in-phase susceptibility measurement, which means that the diamagnetic signal of the single crystals. That one, so you see this is the 1 Oersted excitation. Previous measurement for the vortex glass study, we had to go to much lower amplitudes to have low probing currents. In this case, we used higher excitations, and this is a zoom of that anomaly which I showed. So what we have zero field cooling, and after field cooled, the warming. So we see also the irreversibilities in the vortex dynamics in the single crystal. So this is the out of phase and this is the in phase. And this region is quite interesting, meaning that at the same magnetic field with decreasing temperature, you lose a little bit of diamagnetic signal. Now, when I moved to a higher excitation, bam, got like this. Again, this is something which I can discuss in other terms, different phases, single multi-grain. 10 years ago in Japan, I also had 2 peaks which were changing very interestingly in different magnetic fields, and it turned out to be the sign of a multi-component superconductor, which later on was found in many other systems. So our work with Yasumoto Tanaka in 2009 was confirmed later. But this one is quite interesting. Now this is huge. This anomaly is huge. So this is again in 1 Tesla. Now it has just a 10 Oersted excitation, and you have the normal going down, the diamagnetic signal, and suddenly the diamagnetic signal decreases a lot, meaning that from here to here, with decreasing temperature, I lose a lot of the diamagnetic signal, so meaning that I use a lot of critical current density. We repeated this also at other fields. Now the difference between this one and the previous one is that most likely with this low field amplitude, the vortex is mainly in the Campbell state, in which it oscillates just inside the potential well of the pinning center, while when we put 10 Oersted, so a much higher excitation, it can go out of the pinning well. So this happens also at 3 Tesla, 5 Tesla. Okay, so this is 3 Tesla, 5 Tesla, and in 7 Tesla it starts to fade off the effect, but we are now probably going towards a wipeout of this anomaly. Of course, we studied this also with Dc Magnetization Loops. Now, it is known that these single crystals have second magnetization peak, but in usual single crystals with second magnetization peaks, and you will see some of examples in the poster of Alina Ionescu downstairs, in which there are other types of single crystals, including Pnictides, and including one of the crystals which was provided to us by Tsuyoshi Tamegai. You see, we have also intersections between DC magnetization loops. So usually in some other types with second magnetization peaks, you have magnetization loops, one in the interior of the other and one in the interior of the other one, but it was never reported intersections like this. So this is between 4 and 14 Tesla, between 4 and 14 Kelvin. I'm going to minus because in our PPMS, if you go to positive fields, you can get some problems. One of the thyristor was not functioning properly, and Quantum Design said that they don't have spare parts for that, so have to buy everything, but that everything is too expensive. So we go to minus 14 Tesla and to positive fields up to 8 or 9, not more than that. So this is quite intriguing also. Now, we also started to do some preliminary magnetic relaxation measurements. So again, we use the normalized magnetic relaxation rate and the normalized vortex clip activation energy. So we have a characteristic pinning energy, in which, of course, the width of the magnetization loop as a function of the magnetization as a function of time is proportional to the current density as function of time. And in this formula, in the follow formula, JC is the creep-free critical current density. So the normalized magnetic relaxation rate, which we also saw in the previous talk, but in that case it was about the strong pinning centers only. It's given by this formula, in which we have a relaxation time window. And if we define the effective vortex clip activation energy as U star, which is temperature divided by a normalized relaxation rate, and we have these dependencies. So temperature dependence is a logarithmic one with P is a creep exponent, and the current dependence is again this one, with the creep exponent being positive for elastic creep and negative for plastic creep. So we have these values, plastic creep -1, and for single vortex creep This one, it is in theory to be -1. So these are the preliminary results. First one, we have U star as a function of field for 25 Kelvin. And you can see 25 Kelvin is where the, let's say, the normal behavior still active, but starts to change into anomalous behavior. And in 1 Tesla, the temperature dependence has a quite strange behavior. For normal single crystal with second magnetization peak, you have something like this, in which you have a crossover at some point between elastic trip and plastic trip. In this case, we have positive slope, then negative slope, then again a positive slope up to 25. We didn't measure further, and we have to repeat these measurements and to take many more temperatures, and we can do that now because our SQUID MPMS machine is now functioning. Other measurements have been done at 3 Tesla, and again we have some interesting differences. And you see this is the 3 Tesla AC measurement, and you can find some correlations between these curves here. But I said, as I said before, the magnetic relaxation measurements, they have to be completed and repeated and made for many more temperatures to get a, let's say, a conclusion about what type of vortex dynamics can we imply for this interesting anomaly in the vortex dynamics in this type of single crystals. So I will leave you with the conclusions because my time is out. Thank you very much for your attention.
Thank you for the perfect timing. So